A lot of research going on there, and what I'm concerned the most is this part of the propagation modeling there, and we also have other things like medical applications, and also this one is detection of unexploded ordnance, and also all these communication test bed. And recently we have like directional networking for rural areas, and in Hawaii, some islands, we don't have good communication. So that's what we are trying to do. And plus machine learning, which is we're trying to save energy. Like if you have a network, how to operate this one with the least energy you need. So that's optimization problem in terms of machine learning is just how to learn from the experience. We're trying to use reinforcement learning to do the task. And many others. Also, we have education in for high school. That is the entire Hawaii state. Tens of middle schools participated in this project. Okay, so that's the Hawaii Center for Advanced Communications, and this one is the website we recently updated. So this one is several pages, photographs, I think, in the first page, and we have some facilities there and some books we recently edited. Okay, so the outline here, first talk electromagnetic waves and wireless channels, and then we'll look at why we do propagation modeling or channel modeling here, and wave propagation mechanisms and the geometrical optics, and to see why we need the geometrical optics for the calculation of signals. And then you introduce the ray concept and the ray associated fields. And in that case, we'll try to solve a very complicated problem using a simple method. And then the most useful parameters we need is a path loss here or path gain in the large scale propagation model. And that's when we measure or when we simulate, we calculate a path loss or path gain. And then the ray tracing method, and it is just the method we're using to simulate all the electromagnetic wave propagating there. And then also you need to know how to model the environment, because if you don't know how the environment is, and we cannot do the simulation. So that's a very important part. And then the ray tracing is famously slow, so we need to accelerate if we need to do some efficient simulation. Of course, conclusion and then acknowledgement. So that's the brief outline. Any other questions? So electromagnetic wave and awareness channel, and we can start from electromagnetic wave here. And wave is just like water wave, sound wave, we can see or we can hear. And the electromagnetic wave, particular case is the light wave, we can see it. And any wave, they need some medium to propagate, like a sound wave. We need the air to propagate. If you put something, if you don't have air like outer space or in a vacuum, sound cannot propagate. And electromagnetic wave is the same thing. We need some medium to propagate electromagnetic wave, which is the electromagnetic field. And then the waves can travel in many ways, like a straight line, and they can go through some objects, like transmitted. If I speak here, maybe other places they can hear me. That's the transmission. And also, it can be reflected by objects, just like sometimes you get echoes, so that's the reflection effect. And also, we can go around obstacles, that's what we call the diffraction there. So that's the features a wave can do, and that's just several features here.
And we also know if you have two waves, they can interfere each other, resulting in very strong or very weak waves. So probably in high school you do the sound like you have two fork, right? You knock them with different frequency and you hear ooh something. That's the interference. So in here, if everyone is speaking, actually we all have sound waves emitted. So in that case, if we speak, similar level of loudness, then we cannot hear each other. So that's the interference of waves that can cause. Electromagnetic waves they do the same thing. So in this room, probably I think there are many waves are going on here, although we don't know. At least everyone's cellular phone will emit some signal, even if it's in a sleeping state. So a lot of waves in this room, light waves, electromagnetic waves, any kind of frequency. So they just interfere. That's a very important feature, and the coexisting waves can give very complicated resultant strength distribution. So if you have many waves act together, and some add together strongly, some add together like a destructive way. So it's a very complicated structure in the final state. And electromagnetic waves are complicated because the electrical and magnetic fields, they are all vectors. Its sound wave is simpler, but electromagnetic wave, they are more complicated. And it is usually very difficult to predict the electric signal strength, even if we know the source and the environment. So if we know this room and if I ask what is the electric field strength here, nobody can answer. That's the problem. Even if you know the problem, you cannot solve it. That's the issue we have here. So this one is just some features. So electromagnetic wave, theoretically, the Maxwell's equations is a general law we need to represent electromagnetic waves. So that's the general rule here. So I just give you 4 equations, and if you see this one and you laugh, then you are in the electromagnetic field area. If you never saw this one before, that's okay. They are just Maxwell equations. The 4 equations, if you know that, all the electromagnetic waves, they obey the equations. No exceptions. So that's the law, and they obey. So that's a very important equations set here. And from Maxwell's equations, we can derive a wave equation, which is can be expressed a simpler way, but with only 2 equations. From 4 equations to 2 equations, simpler a little bit, but the differentiation is more complicated. It's a second order differentiation now. So that's the 2 equations are for representing electrical wave and magnetic wave. Actually, they act together. And then if we know the boundary conditions, which means that if we have some source like antenna emitting some electromagnetic waves, and we want to know the boundary of that wave, for example, in this room, electromagnetic wave has a boundary here. So the wave can go through the boundary or just reflected from boundary, and that boundary is also an important part of the entire problem. So usually we call the boundary value problem, which means that we need differential equations. Here is Maxwell's equations and the wave equations, and also we need boundary conditions. If we don't have boundary conditions, then the solution maybe are not unique. So boundary conditions plus electromagnetic wave equations, which is differential equation sets. So that's what we need. And unfortunately, that it is very difficult, or in most cases, it's impossible to solve the boundary value problem analytically, or like use a simple method in wireless applications. So in a ideal case, like in a waveguide, we can solve that, but in this room, nobody can solve that analytically, even you don't know the boundary condition here. So that's a very important problem we need to solve, but the traditional method does not work. Okay, so then what is this? If we want to characterize the channel, right? If we want to know how the wave propagates, then we have to make sure that we know what we are looking at. For example, usually we look at small scale fading, like in this room, and this one is the floor plan. We have a source. I think this one is supposed to be the transmitter here, and all these red colors and the yellow colors and representing the signal level. Red one, they are high, so when you are close to the source, you see more red spots there, so the high energy there. And then if we look at the field distribution along this line here, and what we saw is something like that. If you go through that line, or walk through that line, you see signal changes very severely. So this one, this kind of a change in the length between the top, like at peak and the valley here, is around half or several wavelengths. That kind of change is very fast. And in time domain, we call this one fast fading. In the distance domain, we call it small scale fade, severe change. And this one actually is what we measured in University of Nottingham, Malaysia campus. You can see the signals in the hallway, they change very fast. This one is just going from 1 meter to 20 meter, so the signal changes very much. And if we look at the details here, around here, that's from 18.8 meter to 19 meters. So it's a 20 centimeter scale here. You can see how they change. If you are familiar with the dB scale here, they change from here to here, like 20 dB, which is a very severe change, the signal change here. So that's the small scale fading. And another one is the larger scale fading, which is a signal variation in a much longer distance. Actually, if we average all these signals along some distances, we get the larger scale fading here. So it is usually, when we average them, small scale fading, they disappear, and what left, you will see the variation, still variation there, but they're representing the larger stuff, larger buildings, hills. They have some effect on the variation of the signals. For example, this one is, we have the larger scale fading. If we just use the two lines to represent them, and this one is just the propagation feature in this particular environment. Okay, so that's how we characterize that in terms of path loss. And then we also need delay spread. For example, if we have, if I speak here, if we think of in terms of sound wave here, you see that I can hear some echoes. These echoes are just like the waves here. So if I send out the electromagnetic wave, the first signal goes to the receiver, and then some other signals going other way, like bounced by the walls, bounced by floors, and they come later. This one is the time. So if you receive the first signal, then you will receive many other echoes. Now these echoes are here. Sometimes they are not good, sometimes they are good. So that is why we need to characterize all these things. If we see too much echoes, then how we can avoid that, or in terms of exploit them, how we can combine them into some useful energy. So that's another story. And also angle of arrival, for example, in which direction you can hear more, in which direction you can receive stronger signals, things like that. So in terms of angle of arrival here, we can see the same signal profile from here to here. We just plot them in a different way. This one is the angle of arrival, which means that in that direction I can see a strong signal, but in other directions you don't see any signal there. So that's also the spatial, in space, the characterization of the multipath. And then the transmit. So the wave transmitted from a source can go from one location to another location based on different mechanisms. So here, like a direct ray, without any interaction with the environment, and reflected, transmitted, we saw that before, diffracted around the edge or corners, and scattered, which means that if the surface is rough. And also the combination of all these mechanisms. Some rays go through reflection and then transmitted and then diffracted. That kind of combination is possible. And also all the mechanisms can happen several times. It can be reflected many times. And the point here is that it is very difficult to determine the signal strength using analytical or four-wave simulation methods. So this one is where our work is on. So if we don't know how the signal distribution is in a room, then it is impossible to build a wireless system efficiently. So that's how we need to know that. And then geometric optics is just the tool we want to use. And geometric optics we all know from high school or even middle school physics, right? When we have like a lens or glasses, and we can do some very interesting experiment. So it is very successful before electromagnetic waves theory. So, but geo itself is not enough for the calculation of electromagnetic wave in a complicated environment. So here we need to extend the geometric optics. So first we know the electromagnetic wave and the light, they are unified by Maxwell. And then the geo is just a high frequency solution for electromagnetic wave theory. So that's the second assumption here. And then for electromagnetic wave, they are complex waves, so it has magnitude and phase. In geometric optics, traditionally we don't care about the phase, but in the extension we have phases added. And then the diffraction is also added, geometrical theory of diffraction. And most recently we have the uniform theory of diffraction. They all add together. And most important principle in this geometric optics is Fermat's principle of least time. It was invented a long time ago, but it's very simple. So it's just a light travels along the path that takes the least time. So it's a very simple principle, and we can do it. If you drive a car, you try to find out the shortest path. But the light here, it is small enough, you can always find out the shortest path from one location to another location. So that's the way we can solve many important problems. And the fundamental method to determine rate paths, this Fermat's law is a very fundamental method we need. Okay, so then Klein and Kay in their very famous book, they mentioned that if we can solve Maxwell's equation, that's very good, but you can see that it is well known that Maxwell's equation can be solved exactly for few problems. So just as I mentioned, in this room, nobody can solve that analytically or even use a numerical method. So that's why we pursue some method based on the geometric optics ideas. So that's that. So I'll just give you a very simple illustration how we can use geometric optics to solve electromagnetic problems. So this one is a source, and imagine this one is a point source. All the energy is coming out. So if we look at one particular cone, the energy is going through this cone, and we assume the cone does not leak out. So how much energy going through here is equal to how much energy going through the next cross section here. So based on this one, in the center, we'll introduce a line from of this center of the cone. We call this line the ray. So that's the ray concept we introduced. It's a very simple idea. And then you can see that if we look at some field at this location, and then we can calculate the field in the other location. So that's the basic idea. We solve electromagnetic wave problem using the geometrical optics method. So based on how much energy you have in these two locations, we can relate the electric field E here at location R and location R sub-zero there. So that's how we can do it. Just use the equation here, which means that how much energy going through the first place here, this cross-section, is equal to how much energy going through the second cross-section. So that's the equation we need. And then based on that, we'll get the equation like that. So this one just relate the electric field at location R and location R0. So this one is related to this one. That's it. So this one means that we can solve Maxwell's equations, 4 Maxwell's equations you saw before, and we can solve it with this kind of simple method. Everyone can understand that. That's how we can solve it. So that's the idea here. So in that case, we can get this equation does not have this term. This term is the phase term we need. So we can just add it to it. That's the complete solution for this electromagnetic problem. So this one is also the field calculated in this way. We call the wave-associated field. So that's the idea. Okay. So what is the path loss and the path gain? And that's the parameter we need for channel characterization in terms of a larger scale term here. So it is just path loss is just how much transmitted energy. If we know the received energy, so the ratio of these two values is the path loss, which means that if you explain this one in terms of you invest, right? You invest like $100, and how much you get? If you get like $90 and later, you lose money. If you get like $120 back, you earn money. So this path loss is just a ratio of that. So if path loss is greater than 0, which means that your gain is less than what you invested. So the other one is a path gain. Loss and the gain, they are just inverted. So we just invert the ratio. So now the received power over the transmitted power is the gain. So that's a simple definition here. And for the free space path gain model is just like that. So here we have 2 parameters, lambda here and d here. Lambda is the wavelength. The wavelength is the electromagnetic wave. It has some frequencies, and then we can define a wavelength. And distance d here is from transmitter to receiver. So here you can see that if we have this distance increases, then the power gain decreases. This one is very intuitive, because when you go far away from the transmitter, you receive less and less power. So that's what we can see that. But it is over d squared, which means that when your distance increased by 10 times, and your power will decrease by 100 times. So that's a huge loss. And also it's a function of this wavelength. Wavelengths, maybe if you know wavelengths, that's easy to understand. But here, which means that if you have a small wavelength, then the power gain will be small. If you have a large wavelength, then the power gain will be large. So the wavelengths and distance, they play similar roles, but one is positive, another one is negative. So that's the power gain here. Just give you some idea. So we know that currently we're using like 2.4 gigahertz, like in the cellular phone, or 5.8 gigahertz, especially in the Wi-Fi, right? And we know the wavelength is inversely proportional to this one. So longer wavelengths, shorter wavelengths. This one is a lower frequency, higher frequency. The wavelength decreases and frequency increases. And this one, this term, we just set d equal to 1 meter. So what does that mean? Which means that if you have an antenna somewhere, and 1 meter away, if your frequency is 2.4 gigahertz, then the power at that 1 meter away is only this much times your transmitted power. It's very, very small, right? it is more than 10,000. If we just run this one to here, it is like 10,000 times smaller than that. And when the frequency goes up and the wavelength goes down, and this one is getting smaller and smaller. So that's the idea, which means that if you use a higher frequency or longer wavelength, shorter wavelengths to propagate some signal, you need more power. It cannot propagate long away. So that's the idea. And also we can plot previous things like that. So this one is distance in the wavelengths. And if you are one wavelength away from your source, and this one is the source is weakened by this much. This one is up to the -3 here. So 6.33 times 10 to negative times of the 1 here. So that's the same figure we have in the previous slide. If in the decibel or dB scale, you can see the same trend. But for engineers, for electrical engineers, especially in wireless communications, and we know if you go away from the source by 1 wavelength, the signal is deducted by 22 dB. That's a very severe signal change deduction there. Okay, so how to get the array? And if we don't have any complicated environment, for example, if we have a transmitter here, receiver here, and we have a direct array from here to here. So that's a very simple idea. But if you have some object, we can get a reflection from here. So that's the idea here, how we can determine this reflection from this surface here. So this image method is also very intuitive, but very important and very fundamental. We can do many research and calculation there. So I just want to show you a little bit. For example, if we just imagine this one, this surface is a mirror, and this one is you stand here, you see your image here, right? So that's the image method. Very simple. So then we got an image here, and that's the image behind the mirror. And then we connect the image with this receiver here. We connect that, and we got intersection point here, which is actually the reflection point we found. So you can see that the real reflection will go, the electromagnetic wave will go in this direction, reflected at this point, and it goes here. And the principle here is just the famous principle of least time, which means that when the light travels along this path, it takes the least time. Or the path, the entire length of the path is shortest. If you go like reflected from here to here, or reflected from here to here, they all have longer distance. And this point gives us the shortest distance the light can travel. So that's a very smart way light can do there. So that's and I believe the light is smarter than us. we can always find the shortest way to go from one location to another location. But light knows that. And they don't even have to calculate. They just go. So very intuitive, like genius. Okay, so this one is just, by the way, we can prove that if you are a little bit like mathematics, and we can prove this one. For example, if I select any point, which is not this point, so you can see that based on the image, right? So this distance and this distance are the same. So if we travel from here to the receiver, is equivalent to we travel from here to the receiver, because this distance equals this distance. And then you can see that travel from this location to this location, the shortest path, of course, is a straight one, right? If you go this way, it's longer than this one. If you go here, and it is longer than this one. So this one is definitely the shortest path we can have. I'm not sure I want to show this one here. This one is just a more complicated case, because we have several surface. Maybe I'm not sure. Maybe I can just skip this one. So finally, we can use the image method to get this one. This one means that if you have a source here, which is behind this object, and receiver here, how can we find an array that comes from transmitter to, any way and arrive at this receiver here? So actually, we use the image method. We can find a way like that. This array is mathematically correct, and we can use the image method to do it. And we can just draw it, and it's very easy and intuitive. And this one is an example for arrays, how the arrays travels. This one is a transmitter. If we launch an array in this direction, if you remember the ray cone, right? When the array is coming out, it's getting larger and larger, it's spreading out. So in this direction, you can see at this location it's very thin, and it's getting wider and wider because of the spread effect. This is just one ray we launched in this direction here. And then when this ray is hitting this wall here, it got reflected. So we have a ray in this direction here. That's the reflected ray. And some portion of the ray is transmitted through this wall here. That's this one here. And then in this direction, it got reflected in that direction here, transmitted further, and reflected here, things like that. So all these sub-rays, you can see from starting from this one, and we got all these rays. They are just has the same ancestor, originated from the same one single ray we launched. So you can see how complicated all these rays can come, and that's the way we are trying to solve the problem using this method. And then this one is the rays in a city, many buildings, and if we have a transmitter at this location, I think, and then we launch many rays, and some of them can be received by the receiver there. So that's one example here. I think I have animation here. Let me see if we are okay. So this one is a three-dimensional environment. You can see that. It's a 3D building. We have a transmitter here. We see the transmitter here, and receiver here. Receiver, we are going along these lines. So if I let it go, you can see that at some point, this one here, for example, and this one is the receiver, this one is the transmitter. You can see many rays going from the transmitter to the receiver, and you can see that from the top, and you can see many rays, which is, let me see. So that kind of ray, you can see it's a three-dimensional case, and you can see how many rays going through all these structures, buildings. So that's just an example we can have, and that's the ray we can have. And based on the rays, we can calculate the electromagnetic field or the signal strength path loss along the different locations. That's how we can do it. By the way, all these pictures, we put them in Google Earth, so you can see it in Google Earth environment. Okay, so that's the example of rays. And then we also need to model the environment. And for the terrain, we have this SITM here, which is United States. They did it in, I think, in 1980s, I think, or 2000 here. And get it, the entire world is mapped. And in US mainland and US territory, they have very accurate or high resolution maps. In other locations are a little bit less. So that's the physics here. We have a shuttle, and the shuttle carries a very long antenna here at this point. So when the two antennas they illuminate the Earth, they got two interference signals. By the interference, we can deduct the height of the terrain. That's the elevation data we got. So this one is an example for the environment, which University of Hawaii is located there. So that's the data from the SRTM database. It is open, you can download it, and it is free. And if you want to look at this data, you can download it. Okay, and also we have Google Earth, which is the product of Google company, and they have three-dimensional buildings in many cities, like this one here. Based on that, we are able to extract the 3D buildings for our use. For example, this one is in the Waikiki area in Honolulu, and this building we extracted to this one here. We ignore some details. We got the most important features for the propagation modeling here. So that's what we can do. And this is important because if you don't know the environment, your simulation is just baseless. So that's the key part of the simulation. And then the ray tracing is very slow if you don't do some acceleration work. So here we have using the two methods, we divide the entire environment into small rectangular cells, or we divide them into very small triangular cells. By that, which means that we know the structure of all these objects, because we have a network here connect all these objects. We know the information of the network. So that kind of acceleration makes the practical ray tracing possible. And also we can use the object division here. We divide the different objects into different groups so that the ray knows in which group it is traveling. We don't have to visit other groups. So that's an idea we have here. So these are just some research results we have. And we can also use a GPU, which is a graphics processing unit. So that's compared with CPU. We know CPU. GPU is just a graphic cards. In that case, for this example, that we can program the GPU here to accelerate the calculation. So this example I used many times because here we're trying to calculate the entire Oahu Island if we have a transmitter put on this one here. So entire Oahu Island is this area is about 70 kilometers, and this one is about 55 kilometers. So that kind of a scale, you can imagine how large it is. And using the ray tracing method, we're able to do that and in a very fast way. So here, I just used this laptop. It's about 7 years ago, 7 years old. The laptop is very aged here. And then you can see how many points we have. It's almost 500,000 here. And the entire calculation time is 0.154 seconds, which means that the internet just calculates, and you immediately see the result. So that kind of a speed, which means that in terms of how many points you can calculate per second, it's 3 million points. You can imagine how you can do 3 million things in 1 second, right? So this is the acceleration method. We use the hardware, and we can get that kind of a speed, which is fast enough to do some real-time simulation. So that's a very important achievement we did. And then, of course, if you want to do ray tracing, you will need a computer to do it. And then a programming language is very important. So here I just give you some example. I used in the research here. We have C, C++, Fortran, and Python, OpenGL for the graphics, and so on. And also for the operating systems, we can work on the Windows, Unix, or its sister like Linux here. And we did a lot of work in indoor environment, urban or outdoor environment, or the complex one, indoor to outdoor, and the terrains, mountain areas, atmosphere, And we're also using the genetic algorithm to optimize the base station locations if we want good coverage. Okay. So this one is some examples, like Staywell, and Dr. Grace did a lot of work in that area. And the right one is the fuselage for airplane, and you can see the rays there. And this one is a software we developed, the GUI of that. This one is for indoor simulation. And one graduate student just developed this one for the user interface. And the radiation pattern of the antenna is considered, and you can move the rotate the radiation pattern in any direction you want, and things like that. And of course, we did some work in the atmosphere wave propagation, and you can see the rays in the atmosphere is not straight anymore, because the atmosphere, the index of refraction changes as a function of the radius to the center of the Earth. So that's why it bends when you travels in certain directions. And even they can trapped in a duct. We call the duct effect here. Make sure this one is a kilometer here. You can see the wave 100 kilometers, 200 kilometers. That is a very long distance. And sometimes we can have wave goes around the entire Earth, right, several times. So that kind of propagation effect. Okay, so for indoor cases, we're also interested in the direction of arrival or direction of departure. That is animation here. You can see in this direction, we also have the longest distance with strongest received signal. So that's the direction directed to the transmitter, line of sight. Of course, we again the rays we can do it, and then in this case, the entire Oahu Island we can put the result just overlay on the Google Earth software, so you can see it. So that's the with the GPU there. And then we have some validation. If you want to say your software works well, you have to compare with the measurement. So this one is a resin in Virginia, and it has measured data by military applications. So we can compare with them. The red one is our result. The black ones, there are several black ones. One is measurement, the other one is the simulation by other groups. So you can see all these results they look similar. So that's an indication of accuracy here. And we also have the Munich city. This one has thousands of buildings, so it's a very tough problem. And you can see we compare with the measurement. The blue one is the ray tracing result, and the red one is just the measurement. So basically, we can catch the most important propagation feature here. And then the indoor cases, this building is where the office is, so we can measure in the building very easily. So you can see that the red one and the blue one. Red one is just the ray tracing, and the blue one is a measurement. So they match kind of good, very well matched here. So conclusion, and ray tracing is just very important, and it is suitable for large-scale propagation modeling, urban indoor mountains. Naturally, we have all channel parameters like path loss, path gain, angle of arrival, angle of departure, and delay spread, and so on. All the spatial and time domain features we can catch with the ray tracing method. Other methods they don't have all of these informations. Even if sometimes they can do some work in a small area, but they don't have all these parameters together. And especially it is useful for 5G, fifth generation communication system, because for 5G we need the spatial like time delay or angle of arrival to make the receiver wireless system more efficient and reliable. So and then a realistic environment we can model that, and with very good accuracy, and more importantly that we can model the environment in different levels of detail. So sometimes we don't need some features of the buildings, for example. Sometimes they're important. So that's the different levels of detail we can implement in the software. And of course, acceleration of the ray tracing is a key factor for your method to be useful in the applications. And finally, the programming language affect the efficiency. If you use like MATLAB, it will be very slow, but if you use like Fortran or C++, it will be 100 times or 1,000 times faster. So that's the case. Acknowledgement, after Professor Grace Lim, she's here and she proposed the project and get everything down, all the logistics she did. Thank you very much. And Professor Vincent Lim in MAU, he just let us use his equipment for all the measurements we did in the past 2 or 3 weeks. So that's a very generous gesture. Not easy to do that. Not many people can do that. So that's very important. Of course, MCMC and all of you here and helping me a lot in organizing the workshops and also all the funding here. So thank you very much. And Fulbright specialist program, yes, and also MSc, and they have guidance how I can do this one and do things like that. I don't know. And what the learning helped me just apply for the specialist program and a lot. And some students, them here, like Daya and him here, right? Yeah, Chong. They did the measurements and very successful measurement and very hardworking and very motivated students. Thank you for your work. And thank you all for attending the T-Talk. And this one is the first time I came here. Thank you again. So, and I think you're the happiest one. Yeah, we have some like a measurement here, measurement in Nottingham University, and all of us, and Grace and students, and also I'm trying to fix something, I don't know. Yes. Okay, well, this was yesterday we had a meeting in the university for discussing for the project and the possible future works, something like that. And also have in the KLCC, the tunnel, the more than 100-meter long tunnel we measured there, and you can see the transmitter here and transmitter here. And several students, they are carrying the antenna going in that direction. So they one measurement, they walk like 100 meters. How many times you did? At that time I wake up 3 o'clock, and the students and Grace, they did not sleep. So they kind of they're too excited for the project. And we finished in the room, right? So that's a very exciting work and a very important result. I just showed one result there, so that's a very useful measurement. And next time if you go there, you can say, oh, boy, I saw somebody measured something here. So that's the very famous tunnel. And that's one student, Chiping, he's not here, and we're trying to align the transmitter and the receiver at the beginning, like after measurement. And finally we got it, so everyone is happy. Okay, so this one is in Multimedia University, and I gave a talk there. So afterwards, they give us some souvenirs. So that's our professor. So he is the professor, gave us the equipment for the measurement. And last time in the workshop. Again, thank you again. You introduced me and gave me some confidence to do that. Okay, this one is in ray tracing. So that workshop is much more technical, and so that's the case. And that's the audience in the conference. And we have some pictures with the Multimedia University. Okay, so hope to see you in Hawaii. Thank you very much.
Do you have questions to start?
Any questions?
Prof, just one I think you have shown one card that shows